Good morning. So here we are talking about Chapter 8, the alkenes, and how we can make an alkene. We've already talked about what we could do in Chapter 7 with the substitution reactions, where we can do either an SN1 or an SN2, depending on the conditions on a good leaving group to form a substitution reaction. We can also do the equivalent of that with eliminations, where we either do an E1 or an E2 reaction. So during this chapter, we'll talk about that and refer back to what we talked about in this substitution chapter about what all we can do for that. So the first thing we need to do is talk about nomenclature of alkenes, and we need to be careful how we number them so that we get the alkene with the lowest possible number, and we need to use either cis or trans or E or Z for the alkene when we have to. Okay, cis and trans we can use only if we have a hydrogen on each end of the alkene. E or Z works with all alkenes, so if you want to use E or Z, feel free. So this first one is an octene, because we have an 8-carbon chain. It is the double bond is on carbon 3, and then off of that we have a 2,5-dimethyl 3-octene. Okay, and in that we also need to specify what kind of alkene it is if we were to draw a line through the double bond and look at where the groups are off of each end, the big groups. If they're on the same side, it's cis or Z. If they're on opposite sides, it's trans or E. So this would be trans 2,5-dimethyl 3-octene. The next one, we have 2 hydrogens on one end, so they're the same group, so we don't have to say cis or trans. All we have to do is number to say it's a hexene, and then it's a 1-hexene because the double bond is starts on carbon 1. Okay, we always, on the straight chains, we always have to put the number in there. We cannot assume anything. In C, we have to number through the double bond, so it is going to be a 1-cyclohexene, or we could just say cyclohexene, because it has to go through the double bond, and the double bond, since it's the only functional group, it has to be on carbon 1. So here we don't have hydrogens on either end, so we need to look at what we have. So 1, 2, 3, 4, 5, 6, 7. So this is a heptene. On that, it's a 3-heptene, and we have a 3-bromo 4-methyl 3-heptene. And then we need to look at the double bond, or the big groups. On one side it's the bromine, on one side it's the propyl, so they're on opposite sides, so it is a E 3-bromo 4-methyl 3-heptene. Here we have hydrogens on either side of the double bond, so we could say either cis, trans, or EZ for that. We number 1, 2, 3, 4, 5, 6, 7, 8. So it is a cyclooctadiene, because there are 2 double bonds. The double bonds are, you have to start with a double bond and number through it going to the next one. So that's why it's a 1,5. Sorry, let's put it over here closer. So it's a 1,5 cyclooctadiene, and then off of that 1,5 cyclooctadiene, it is a 1C5Z 1,5 cyclooctadiene, because the double bonds, the big groups, are on the same side of each one. The next one, we look at the ethyl versus all this stuff. So this double bond is an E, and we look at the bromine versus this. So this double bond is an E. Then if we erase all of that so we can talk about what we have. If we start numbering 1, 2, 3, 4, 5, 6, 7, 8, 9, it's a nonadiene, and it is a 3,5 nonadiene, and then it is a 5-bromo 4,6 dimethyl 3,5 nonadiene, and then it is a 3E5E 5-bromo 4,6 dimethyl 3,5 nonadiene. For alkene stability, the more substituted, the tetrasubstituted is the most stable of them. So it'll be the one that it would react the easiest to reacting as a nucleophile, because it would form the cation most stable. So in this, possible mechanisms for the elimination, just like in the substitution reaction, we could see it happening all at once, where the base comes in, grabs a hydrogen, forms a double bond, kicks out the leaving group, all in one step, or, and that's an E2, just like the SN2, everything happened at once, or we could have the cation, the leaving group leaves, forming the cation, and then the base comes in, grabs the hydrogen to form the double bond. And in these, that's the E1, because we went through the cation. So the E2 is a direct displacement. The E1 goes through the cation. And if you mix them up or draw a cation and an E2, you've drawn it wrong. You have to be very careful how you draw them. So the E1 reaction would work best with the tertiary one, because it is the one that's going to form the cation the easiest. And it's all about the stability of the cation, the ability to form the cation that makes the reaction. So if we write a mechanism for this, if we look at this, we have 1, 2, 3, 4, 5 carbons in both. And the carbon with the chlorine was this carbon here. So if we look at what we have to start with, we have 2 hydrogens on the first carbon and the second carbon. But here in our alkene, we have 1 hydrogen on the second carbon, but we still have 2 on the first carbon. So in this mechanism, our base has to go grab a hydrogen, form the double bond, and kick off the chlorine. The hydrogen that it grabs has to be on the adjacent carbon to the carbon with the leaving group. That's the only one that's reactive. So in this mechanism, we have 1 peak. We're going to go from starting material to product. And here in our transition state, we have the bond breaking to the chloride, bond breaking to the hydrogen, the oxygen forming a bond to the hydrogen, and then hydrogen going back, hydrogen coming, whoops, one of those is an alkyl chain, doesn't matter which one. And then we have the 2 hydrogens going back and coming forward. So here's our transition state, and in this, the chloride is leaving as a partial negative, and the O- is coming in as a partial negative. And we're forming the double bond, starting to form the double bond there. So all of that is happening at once. The base is coming in as a negative charge. The chloride's leaving as a negative charge. They want to be as far apart as possible, so they need to be anti to one another as they do that. In the E1, we form the cation, and then the base will come in, grab the hydrogen, form the double bond, giving us our product. So in this one, there are two steps to the mechanism. The first one takes a lot more energy. The second one is much less. Right here is our cation transition state, or cation intermediate, excuse me. Here's our starting material, here's our product. This is our first transition state. It's going to look exactly the same as the transition state for the SN1, either of them, because all we're doing in this is we are taking the chloride is breaking off, so it's forming a partial negative. The carbon is forming a partial positive as that bond breaks. So that's transition state number 1. Transition state number 2 is where we have this planar cation, and off of the one of the carbons off of it, in this one it doesn't matter because they're all methyls, we have our methanol coming in, grabbing the hydrogen. So what we have going on is partial positive here, not a full positive, and a partial positive up here on the oxygen as we transfer the positive from the carbocation that we started with in our intermediate to the methanol, protonated methanol in the product. Okay, so the reaction coordinate diagrams are very similar to the SN2 and the SN1. The transition states are different, however, because we're forming different products. So in an E2 mechanism, the reasons why this all happens in one step is that in the effect of the substrate, if we have a strong base, good nucleophile, and the tertiary carbon there, the nucleophile cannot get in to kick out the leaving group to do an SN2 because there's all the steric hindrance around it. So it's much easier for it to come in, grab a hydrogen, form the double bond, and kick off the leaving group because the hydrogen is way on the outside edge of the molecule. So that gives us this reaction taking place along with water and our leaving group with a negative charge. So that carbon with the hydrogen adjacent to the leaving group, that hydrogen is much easier to get to than having the base attack the tertiary carbon with the leaving group on it. So the regiochemistry of an E2 elimination, we have these two. Say we have this where we have a primary hydrogen, the 3 blue hydrogens, or secondary hydrogens, the 2 red ones. Those are the only types of hydrogens adjacent to the carbon with the leaving group. So one of those 2 is what we will take off. If we remove the secondary, one of the red ones, we get the double bond in between the carbon that was the tertiary carbon with the leaving group and the secondary carbon adjacent to it. If we take off one of the primary ones, we get the methylene, so we still have 2 hydrogens on the double bond, whereas on the first one we only had 1 hydrogen and 3 double bonds. And we said earlier that the more substituted is more stable. So of the 2 possibilities, the tri-substituted alkene is much more stable than this one, the di-substituted alkene. So if we can form it, we're going to form the more stable one. And I have these backwards here. Sorry. I need to change that. So with the small base, we get much more of the Hoffman elimination, which is the one that forms the more stable alkene. With the big bases, we get much more of the Zaitsev product, or the less substituted, the less stable alkene. And it's all about sterics in this. If we can form the more stable one, we will. So if we have a small base, we'll form the more stable alkene. If we have a big base, it's much harder to grab that secondary hydrogen, much easier to grab one of the primary blue ones. So that's what happens in this one, in that how it goes. So the small base goes for the more stable, more substituted hydrogen. The big base goes for the less sterically hindered hydrogen. Now, stereoselectivity in this, in an E2 elimination, the major product is going to be the trans alkene over the cis alkene. Okay, and as we go on, we'll show why this is the case. So, in the stereospecificity of an E2 elimination, as we said before, the base and the leaving group want to be as far apart as possible, so the anti-coplanar is the preferred elimination for to form an alkene. And part of this is because we have to form the overlap between the p orbitals that form on each of those two carbons to make the pi bond. So the hydrogen and the leaving group have to be coplanar, either anti-coplanar or syn-coplanar, to form that pi bond overlap. So in this, the most stable one is the anti-coplanar, because the base and the leaving group are as far apart as possible. For it to eliminate syn-coplanar, it will only eliminate this way if you have the molecule held in a certain conformation that it cannot go to the anti-coplanar. So it only eliminate this way if it's held in a syn-coplanar conformation and cannot flip, ring flip, rotate around to the anti-coplanar. Okay, and we have some examples of this in just a minute. So in this, when we look at the reaction below, we see the hydrogen and the bromine anti-coplanar on the compound on the left and the syn-coplanar on the one on the right. So if we were to draw the Newman projections for both of them, if we look this way on both and draw what we see, we would have, for the anti-coplanar, we'd have the bromine up, the hydrogen down. Off of the right side, we have a hydrogen. Off of the left side, we have the T-butyl on the carbon in back. On the carbon in front, we have the phenyl and the methyl. On the syn-coplanar, if we draw it, we have the hydrogen, the bromine. On the carbon in back, we have the hydrogen here, the T-butyl over here. Then we'd have the phenyl over here and the methyl over here. So in these, we can see how as the base comes in, it is very close to the bromine. So the charge repulsion between the O- and the bromine as it forms is very large in this. This syn-coplanar elimination will not happen in this case. It'll only go this way. And if we draw our base, we could just make it a generic base, coming in to grab the hydrogen, form the double bond to kick out the bromine, we can see that on one end we're going to have the methyl and the phenyl. On the other end we're going to have the T-butyl and the hydrogen. So we're going to only get a specific product out of this across the double bond. We will not get the other stereochemistry across the double bond. So in this one, the T-butyl and the phenyl are the big groups. This is the E. We will not form the Z double bond where we have the T-butyl and the phenyl and the methyl and the hydrogen. Not formed. Okay. So the stereospecificity of an E2 reaction on a substituted cyclohexane, for it to eliminate, as we've said, the hydrogen and the bromine have to be anticoplanar to eliminate unless they're held in a certain conformation. In the cyclohexane, it can ring flip back and forth from the bromine being axial to the bromine being equatorial. If we were to draw, looking down these two bonds with our little eyeball and see what we see, if we, so with the bromine axial, if we show the bromine axial, whoops, we have the bromine, the hydrogen, we have a hydrogen going up, and we have the part of the chain. Bromine, we have the chain, and we have the hydrogen going down. So we can see that the hydrogen and the bromine are anticoplanar in this example. If we draw what we see in the other one, we have the bromine looking down that bond, carbon in front, we have the hydrogen. We have on the carbon in back, we have the bromine going up at an angle. Then we have the hydrogen going straight down, and we have an R group, and then an R group and a hydrogen. And we see in this one with the bromine equatorial that there is nothing either syn or anticoplanar to the bromine to eliminate. So this conformation will never eliminate. It can only eliminate when the bromine is axial. Now you're probably wondering, do I have to draw this every time? No, you do not have to draw the chair form and show the Newman projections every time. If you can see that as long as the leaving group is axial, it can eliminate. If it's not axial, it's never going to eliminate. If you can see that, that's fine. You don't have to draw all of this every time. So here in the next example, if we were to look down this bond between the carbon with the hydrogen and the deuterium and the carbon with the bromine and the hydrogen and see what can happen, we would see that the bromine is on the carbon in back, the hydrogen's on the carbon in front, hydrogen, whoops, that's a deuterium, and a hydrogen, and then we have the R group, and the R group of the bicyclic. So when we look at this, we can see that the hydrogen and the bromine are syncoplanar. They cannot ring flip because we have that bicyclic system. So the only product we can form from this is the alkene here with a hydrogen and the deuterium still on the alkene, because the hydrogen and the bromine are syncoplanar. So here we have the elimination of which product are we going to get in this elimination. So we need to draw in our hydrogen and then draw in our hydrogen here and our methyl. So to figure out what's going to happen, we need to draw the Newman projection. So we can think about putting our little eyeball here, looking down this bond. As we look down that bond, we're going to look at the methyl on the carbon in front is going straight down. The bromine is going to our right because we are looking from right here, and the hydrogen on that carbon in front is there. On the carbon in back, just the way it's drawn here, we have the ethyl going up, we have a hydrogen on the same side as the bromine, and we have the methyl, going back. So this is what we have, the Newman projection of the product we were given. Now we have said for it to eliminate, the hydrogen and the bromine have to be anticoplanar. So we need to rotate one of the carbons around. So if we rotate the carbon in back, the one with the hydrogen, 120 degrees, we still have the bromine here, the hydrogen here, the methyl here. On the carbon in back, the methyl becomes here, the ethyl here, the hydrogen is here. All we did was rotate the carbon in back 120 degrees so that we get the hydrogen and the bromine anticoplanar. Okay, now when we do that, we see that the hydrogen and the methyl have to be on the same side, and the methyl and the ethyl have to be on the same side. So hydrogen and methyl, it can't be this product, it has to be this one as the only one formed to show when we get that hydrogen and the bromine anticoplanar. So we have to be careful how we draw it when we have, if we're given the stereochemistry, what can happen in the elimination. So in the E1 mechanism, we said the leaving group leaves, we form the cation, and then the base comes in, grabs the hydrogen, and forms the double bond. So we have to form the cation. So in this, the tertiary cation is most reactive. The tertiary bromide is most reactive, or the tertiary leaving group, because it forms the most stable cation in that. So it will be most reactive to form the most stable cation. So the more substituted the carbon is, the more stable the cation will be, the more reactive it will be. So in this, we have two possible reactions that can happen if we have a tertiary leaving group. The loss of the leaving group happens first in both of them, whether it's an SN1 or an E1 mechanism. It doesn't matter. You form the cation in that SN1 or E1 mechanism, and then the nucleophile comes in to add to the cation, or the base comes in to grab the hydrogen to do either the substitution or the elimination reaction. Okay, so we have to decide what do we have condition-wise to figure out what's going to happen. Okay. The E1 mechanism proceeds similar to the E2 mechanism and prefers the Zaitsev, the more substituted product, when it can form it. The preference is based on the stability of the product alkenes for the reaction. Okay, just like in the E2, the more substituted the alkene is, the more stable it is, the easier it is to form. So in this, we want to, if we can get to it, if we have a small base to take off the extra hydrogen, it's going to go for the most stable alkene most of the time. And what we have in this is, in the mechanism, the first thing that happens is we have to protonate our alcohol to make it a good leaving group, and then it leaves to form the cation, and then we have water around as our base, and water's small, it's going to go for the most substituted alkene, and I lost a carbon on this one, so it's that, so it's going to go for the secondary hydrogen because it's small versus the primary one. So here we have, how are we going to predict the product for the following E1 reaction? We know it's an E1 because we have a tertiary carbon with a leaving group on it. We don't have a good leaving group. we have acid, and we have heat. So we need to identify all of the beta carbons. The beta carbons are the ones drawn large. So it's this one, and this one. The next carbon down the line is too far away. It has to be on the adjacent carbon to the carbon with the leaving group. So we need to look, after we've identified all the beta carbons, is there any symmetry? And in this one, whether it goes above or below down to the CH2 group, those are the same, so that would be the same product. And then the other possibility is we could go out to the methyl. So there are two possible products for this one, whether it goes to a CH2 or to a CH3. So we said before, the minor product is going to be the one to the less substituted alkene. So the major product is going to be the one to the more substituted alkene, since all we have is sulfuric acid and heat in this. Okay. Now, the stereoselectivity of an E1 reactions are not stereospecific, but the E1 reactions are stereoselective. When cis and trans products are possible, the major product will be trans over the cis alkene. Okay. So drawing a complete mechanism for an E1, the leaving group leaves, forming the cation, and then the base comes in to grab the hydrogen to form the double bond. Okay. We have to show the formation of the cation before we do anything else. You cannot draw the base coming in to grab the hydrogen, form the double bond, and kick off the leaving group. That's not drawing an E1. You have to show the formation of the cation. So in the second one, we don't have a good leaving group, so we need to protonate the OH, kick off the bisulfate to make the good leaving group. The leaving group leaves, forming the cation, and then our weak base comes in to grab the hydrogen, form the double bond. So if we have a good leaving group, it's 2 steps. If we don't have a good leaving group, then it's going to be 3 steps in the mechanism, because we have to form the good leaving group before we do anything else. So be careful as you're going along that you think about each step along the way. Now the next thing we have to think about is, do we have the most stable cation in the reaction? In this one, we have the chloride. It can leave, forming the cation. This is a secondary cation. We know tertiary cations are much more stable. So in this one, the methyl can shift over to form a more stable cation, where we went from a secondary cation. When the methyl shifts over, we get to a tertiary cation. So we've changed the carbon framework in this as that methyl shifted to form the more stable cation, and then our base can come in and grab the hydrogen to give us our most stable alkene in between the 2 and 3 carbon of the 2-butene. So an E1 mechanism can have many steps. We have to be careful. If we don't have a good leaving group, like here, we need to form the good leaving group by protonating the alcohol to make the good leaving group. Then it can leave, forming the cation. Once you're at that cation, you have to look around. Is it the most stable cation? In this case, it is not. So the secondary cation is going to rearrange to the tertiary cation, and then our water can grab the hydrogen, form the double bond to give us our product. So we have to look around for what can happen in this, and there are 4 steps that we need to look for in a mechanism. Okay. First, if we don't have a good leaving group, we have to make a good leaving group. So we have to protonate it. Once we make a good leaving group, we can have it leave, loss of a leaving group. We might have to look and see, do we have a rearrangement possible? Did we form the most stable cation possible in the reaction, and then we have the proton abstraction to form alkene. Okay, and we have to, in every reaction, we have to look and see, do we have all of this going on? What can we do? So here we have the reaction we just showed the mechanism for, and in this we get 3 possible products with the most stable alkene 64% of the product, 33% with the alkene after rearrangement but before pulling off the hydrogen, and 3% where it eliminates before it rearranges. So there is not much formed from before the rearrangement occurs to the more stable cation. 97% of it forms once we have the rearrangement to this cation. It's just which hydrogen do we take off? Do we take off the more stable one, or do we take off the methyl hydrogen to form the double bond? Okay, and so those are the things we need to look at with an E1 elimination. We have to form the cation every time. We cannot do it without the cation formation. Drawing a complete mechanism for an E2, we have a strong base. The base will come in, grab a hydrogen, form the double bond, kick off the leaving group all in one step to make the product. Okay, double-headed arrows are required for all the mechanisms in these 2 chapters for substitution or elimination reactions. Okay, be very careful about the type of arrow you draw. Substitution and elimination reactions are always competing with one another, so we have to be careful. What do we have going on? Sometimes only one mechanism will occur. Sometimes we have to differentiate between the 2. With the tertiary leaving group and a strong base, and remember, when you have the sodium, scratch it out, write in the negative charge, because the sodium is just the counter ion. This is a strong base. With a strong base, it has to be E2 or SN2 for a reaction. It can never be an E1 with a strong base. So with a strong base in the tertiary, it's going to have to be an E2 only, because we can't do a substitution on a tertiary leaving group. In the next reaction, where we have a weak base, we have 2 possible products that can form. We can form the alkene, or we can form the substitution product. We can form the E1 or the SN1 product, depending on what we have condition-wise. And that's where we have to be careful about the conditions of the reaction, of what can happen. Okay. So here we are talking about some of the rules of what can happen. And in these reactions, SN1, SN2, E1, and E2, there's not always a clear winner. It might be 2 possible products from a reaction. So we have to be careful what can happen and think about what all we have going on. So the first thing we need to think about is, what kind of nucleophile do we have? Determine the function of the reagent. And the first one, if you have a negative charge on it, it's going to be a much better nucleophile than the neutral compound because of the negative charge on it. So we have to think about, what do we have? So hydroxide is a strong nucleophile, water is a weaker nucleophile. The next thing is, as you go down the periodic table, you get to a bigger atom. The bigger atom is more polarizable. So hydrogen sulfide is much more better nucleophile than water because of this. Okay. So how strong of a base do we have? So here is a table, or the breakdown of the possible things we have. Okay, so the compounds in the first, or the reagents in the first box, are going to be nucleophile only and not act as a base. So these will do substitution reactions. these are base only, and they will do elimination reactions only. The next one, these are strong nucleophile and strong base, so they run the risk of doing either substitution or elimination depending on the conditions of the reaction. And then also with weak nucleophile, weak base, deals with the either substitution or elimination. So the strong nucleophile, strong base is going to be a 2 mechanism, either SN2 or E2. The weak nucleophile, weak base is going to be a 1 mechanism, SN1 or E1. So we have to think about what do we have, what can happen in this. So if we add hydroxide, we know it's a strong base because the pK for the carboxylic acid is about 5. The pK for water is about 16. So the equilibrium is always going to go to the weaker acid and weaker base, which is towards the right. So we won't ever have hydroxide mixed in with the carboxylic acid. We'll have the carboxylate and water. So if we have a nucleophile only, we can either have an SN2 if it's primary, that's all that can happen. If it's a tertiary carbon, it's going to only be SN1. It's the secondary ones that we have to decide, is it an SN2 or is it an SN1? If we have a base only, strong base, it doesn't matter whether it's primary, secondary, or tertiary. It is an E2 elimination because we have that strong base. It's going to grab a hydrogen and take off the hydrogen, form the double bond, kick off the leaving group. Doesn't matter what type it is, primary, secondary, or tertiary. If we have a strong nucleophile, strong base, then with the tertiary one, it's going to be an E2 elimination no matter what. With a primary, it's going to be primarily SN2. With a secondary, it's going to be primarily an E2 elimination. So it all depends on how easy is it to have the nucleophile form the bond to the carbon, or is it much easier for it to grab the hydrogen on that adjacent carbon. If we have a weak nucleophile, weak base, it's going to be, with a tertiary one, an SN1 and an E1, depending on the conditions of the reaction. Weak nucleophile, weak base with a primary or a secondary carbon really isn't very practical. With a secondary one, if we have heat, we can get it to go towards the elimination, but we'll talk about that in a little bit. But there are too many possibilities with the secondary to really just add the weak nucleophile, weak base. So here we are back on this page that we talked about early on in chapter 6. And I was in there a couple of times, and here it is again. So the first thing, the strength of the base or the nucleophile determines the order of the reaction. If we have a strong base, strong nucleophile, it is a 2 mechanism, either an E2 or an SN2. If we have a weak base, weak nucleophile, it's going to be a 1 mechanism, either an SN1 or an E1. Okay, and that one is always going to be that way. It's not going to change. Primary halides with a good nucleophile will be an SN2. With a weak nucleophile but a strong base, it'll be an E2, but it'll always be a 2 mechanism with a primary halide. Tertiary halides, if we have a strong base, it'll be an E2. If we have a weak base, it'll be a 1 mechanism, either E1 or SN1, depending on the conditions. Secondary halides are the ones in Never Never Land. They can go either way. We have to be careful. What do we have? So a strong base, strong nucleophile will go a 2, a weak base, and a good ionizing solvent, water, methanol, whatever, which are in themselves weak bases. It'll be a 1 mechanism because it'll form the cation, and then something else will happen from that. Polar protic solvents favor SN1. They're the water, methanol, ammonia, things like that. Polar aprotic solvents favor SN2, where we have DMSO, DMF, HMPA, ether, things that don't have that proton on the more electronegative atom. Okay, they're still polar, they just don't have an available proton to take off. High temperatures favor elimination. Okay, if you see the delta or heat, your product is going to be an alkene every time. Small bases favor substitution. Big bases favor elimination. Okay, there's no ifs, ands, or buts about that. So here we have another page talking about what can happen if we have an SN2 reaction. The regiochemical outcome: the nucleophile attacks the alpha carbon, the carbon where the leaving group is connected. The stereochemical outcome is an inversion of configuration. If you have a stereocenter, it goes from R to S or S to R. In the SN1, the nucleophile attacks the carbocation, the carbon where the leaving group was originally connected. Unless a carbocation rearrangement occurs, the nucleophile replaces the leaving group with a racemization of configuration if you had a stereocenter. So this one would give you both R and S. This one inverts stereochem. Okay. In an E2, the more substituted Zaitsev product is generally favored. The exception of this is if its sterically hindered base is used, then the Hoffman product is favored. So big base goes towards the Hoffman. A little base is going to form the Zaitsev. The process for an E2 is both stereoselective and stereospecific. When applicable, a trans disubstituted alkene will be favored over the cis. When the beta position of the substrate has only one proton, the stereoisomer alkene resulting from anti-periplanar elimination will be obtained exclusively in most cases. Okay. The Zaitsev product in an E1 is more substituted, is always favored over the Hoffman, and the process is stereoselective. When applicable, the trans disubstituted alkene will be favored over the cis. Okay, so this page, read it over, make sure you know what's going on with it. So here we are. Can you draw a generic reaction and mechanism for the following types of reactions? An E1, remember, has to go through a cation, so a generic one for it would be something with a weak or with a tertiary carbon to form the cation, and then have a base that can come in and grab the hydrogen, form the double bond to form the product. For this one, we would have water and heat as our reagents and conditions for the reaction. In an E2, we need a strong base. So the strong base would come grab the hydrogen, form the double bond, kick off the leaving group to form the product. And in an E2, everything happens at once. In an E1, you have to form the cation. And we have to do those each time, so make sure you remember those mechanisms. In the next one, H3O plus, we should draw it out showing what we have. The double bond goes and attacks the least electronegative atom to form the cation. The hydrogen can migrate over to form the new cation. Water can add to that to form the protonated alcohol. And then Le Chatelier can tell us that we can have water from the solvent come in and take the extra hydrogen to get us to the alcohol. Okay, so it's kind of the opposite of what we do in the elimination. So in this, the next one, we protonate the OH because we don't have a good leaving group. It leaves, forming the cation, and then water comes in to grab the extra hydrogen to form the double bond to give us the alkene. So we can do it either way. We can go from an alkene to the alcohol, we can go from the alcohol to the alkene, and we'll do a lot more of the first one of those when we get into the next test. Okay. So here we have possible reactions where with ethanol we know we want to form the most stable alkene, so with ethoxide, because it's a small base, forms a more stable alkene. And the T-butoxide, it's big and bulky. The major product is going to be where we have the less substituted alkene. Okay, this one's most stable. This is easiest to form. So can we draw the mechanism for the reaction? We form the cation, and then the iodide adds to give us the alkyl iodide. Whoops. Make it bigger. Product, starting material, cation, and our both transition state 1 and transition state 2, they're both going to look the same in this because all we have is the bond between the halogen and the carbon breaking or forming in that. So we have a partial positive on the carbon, partial negative on the halogen. The only difference between the two transition states is it's chloride versus iodide. So this is transition state number 1. Transition state number 2, we'd erase the chloride and put in the iodide. Okay, nothing else would change in that. In the E2, we have the big bulky base. It's going to grab a hydrogen, form the double bond, kick out the chlorine, all in one step. So we have our alkene, we have our starting alkyl chloride. Here we have the transition state, and in that transition state we have the hydrogen, the chloride. They have to be anti to one another because of the charges. We want them as far apart as possible. That may be a little too many dots. Can't tell it's a partial. Hey, and then we have the hydrogen and the alkyl group. And then we have our O. We're forming a bond to that. And then, so our transition state in poorly drawn brackets looks something like that, where we have a partial negative on the oxygen, a partial negative on the chloride. We're forming this bond, forming this bond, breaking this bond, and breaking the bond to the carbon chlorine. Okay, so there's the reaction profile diagram in transition state for the E2. For the SN2, we have the iodide coming in, the chlorine leaving. So iodide is going to be on opposite side of the carbon with the chloride. We have our alkyl group, and then our two hydrogens. So our transition state looks like this, with the iodide with a partial negative and the chloride with a partial negative. Okay. And then the last one, the E1, we form the cation, which is going to look, the transition state is going to look exactly like the transition state because it's the first step of the SN1. We have to form the cation. and then our methanol will come grab the hydrogen, form the double bond to give us the alkene. So it takes 2 steps. The first step takes a lot more energy. Form the cation, and then we go to our products. So transition state number 1 looks exactly the same as the SN1 first transition state. Drawn on the previous page, because it's the same thing. The chloride is breaking off, so we're breaking the bond between the carbon and the chlorine. In this one, the only difference is in the second transition state, we are breaking off the hydrogen, so we're forming this bond between the oxygen and the hydrogen, breaking the hydrogen-carbon bond and forming the carbon-carbon double bond. So to draw it all, we're forming the bond there, we are breaking the bond here, we are forming the bond to the methanol. The carbon has a partial positive here, the oxygen has a partial positive here. We're forming the oxygen-hydrogen bond, breaking the carbon-hydrogen bond, and forming the carbon-carbon double bond. So this is transition state number 2 for the E1 elimination. So I'll let you draw a generic E1 and E2 mechanism. Okay, you should be able to draw one lickety-split without any problems showing everything. When you're done drawing it, scroll back a couple minutes in the slide to somewhere around page 60. This is 68. I think it's page 60 where we drew a generic E1 and E2 mechanism. And it doesn't have to be a specific thing. It could just be 3 R groups or whatever. You just have to show the hydrogen on the adjacent carbon. So in these, how do we tell what type of reaction it's going to be? We have primary leaving group. We have a good nucleophile. So this is going to have to be an SN2. So SN2, 5 carbons with an OMe off of it. Here we have a primary leaving group, weak nucleophile with a strong base. Strong base, it's going to have to be an E2. Form the double bond, give us that. So the next one, we have a tertiary carbon, weak nucleophile, weak base, and we have heat. It's got to be an E1 because of the heat. So the leaving group leaves, forming the cation, and then the T-butanol, since it's big and bulky, will grab a hydrogen off of one of the methyls as the preferred product to give us that, where it's the most substituted alkene. And then this one, since we've done an SN2, an E2, an E1, we have a tertiary carbon with a weak nucleophile, weak base, no heat. It's going to have to be an SN1, excuse me. So the leaving group leaves, forming the cation, and then the methanol adds to the cation to form the protonated ether. And then another methanol will come in, grab the hydrogen, form the double bond, and give us our ether product. Okay, so we look at the conditions, look at the reaction, and decide what can happen in the overall reaction. Draw a mechanism for the following reactions. We have a good nucleophile, good leaving group. We see it's a substitution because we're given the product. All we have to do is draw the mechanism. In any mechanism question on the test, I'll give you the starting materials, I'll give you the products, so you know whether it's a substitution. The first 2 are substitutions, the last one is an elimination. because in the last one we formed the alkene. So all we have to do, since we have the strong base, strong nucleophile, it has to be an SN2. It's going to happen all at once. The next one, it was also primary leaving group. The next one's a tertiary leaving group. We know it's a substitution because we substituted the methanol on there. So it's going to have to be an SN1. So the leaving group leaves, forming the tertiary cation, and methanol adds to it, forming the protonated ether. And then the second methanol will come in, grab the hydrogen, form the double bond, form the lone pair on the oxygen to give us our product. The last one is secondary leaving group with a strong base, weak nucleophile. It's going to have to be an E2. We're going to go for the hydrogen on the adjacent carbon, form the double bond, kick off the leaving group. So here we are, predict the products. So this first one, we have a strong base. So after A, step A, all strong bases do is remove hydrogen. So we're going to take the hydrogen off of the phenol because phenol is very acidic. So we'd get that along with methane, and then the methane bubbles out of solution. It doesn't do anything. And then we'd take this phenoxide, react it with the 1-bromopropane. It's going to be an SN2, and all we're going to get is the propyl phenyl ether. The second one is going to be an SN2, so iodocyclohexane. The third one is going to be an SN1 because we have no heat, so we're going to get the methyl ether off of it. This one's going to be an SN2 because it's primary, so we're going to 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Add the cyanide, displace the iodide. Remember, the sodium doesn't matter. Then the next one is going to be an E2 because we have the big bulky base. So we're going to get the 6-carbon double bond. And the last one with heat is going to be an elimination. And we're going to get that. You should be able to draw the mechanism for each of these. Try drawing them and email them to me and ask about them if you're not sure. Okay. The next page, give the reagents necessary. So we're going about it the other way. In the second one, we see we have the same number of carbons. We just go from having the bromine on the center carbon, the 4th carbon of the 7-carbon chain, to having the double bond. So we just need a big bulky base to do an E2. The first one, we have to first remove a hydrogen off of the nitrogen, so we need a strong base, the methyl anion. And then we need something that can do an SN2 with that good nucleophile of the amidion to give us the propylphenylamine. And then the last one here, we see these 5 carbons on the left, where we formed a carbon-carbon bond to the carbon with the bromine. Our nucleophile would have to be the methyl acetylide. So it does an SN2 because this is a primary leaving group. So all we would need is that for that one. And here we are, the last page of this section, draw some mechanisms. So in the first one, we don't have a good leaving group. We have to form it. So we protonate the OH, make it leave, forming the cation, and then bromide can add to the cation to give us our product. Okay, this is an SN1 because it's a tertiary leaving group. The next one, just along the same lines, we have to protonate the alcohol to make a good leaving group. The leaving group leaves, forming the cation. Those 2 steps are the same because it's a tertiary and we don't have a strong base. And then our Br- or our water will come in and grab the hydrogen on the adjacent carbon to form our alkene. And it doesn't matter which methyl we take it off of, we could take it off either one. So that's an E1 because we have heat and we have the tertiary leaving group. The next one is going to be an SN2 because we have the good nucleophile. So it's just going to come in and attack the carbon, kicking off the bromine, and we're done. Now the last one, since we've done an SN1, an SN2, an E1, the only thing that's left is an E2. On this test, there are 4 mechanisms. You need to be able to draw all 4. They won't be these exact mechanisms, but they will be similar. So in this, we need to look for which hydrogen do we remove. If the hydrogen's drawn in, don't necessarily think it's the right one. Okay, the T-butoxide is going to go for a hydrogen on the adjacent carbon to the bromine to kick it off in an E2. So this hydrogen that was drawn in is still on there. Okay, so don't go for it. If you go for that one, you get the mechanism wrong because it's drawn in as a little trick hydrogen. So leave that one alone. Okay. If you have any questions about this section, send me an email. I'll be glad to answer any questions, talk with you about it as you're going along. Okay. So there's chapter 6 and 7. This is the material on test 3, substitutions and eliminations. Okay. So have a good day, and we'll see you all later.